Welcome, everyone, and thanks for joining us. Today, Dr. Carlos Villaseñor presents us his talk, A Brief Tour for New Techniques in Artificial Neural Networks. He received his PhD from the Guadalajara University. Nowadays, he is a professor researcher and SNE candidate. His lines of research are geometric algebra, encryption, deep learning, meta-heuristic algorithms, among others. At the end of the talk, Dr. Carlos Villaseñor will answer questions from both YouTube and Google Meet. And once more, we thank everyone for attending this talk. Dr. Carlos, the stage is yours.
Thank you, Daniel. So, and thank you to everyone for attending this speech. Let me show you the outline of this speech. Well, first, I want this to be a very introductory, a brief introduction to machine learning and neural networks. First, we are going to discuss what is machine learning, just to be in the same channel, everyone. How do I know if I have an algorithm? How do I know if it's a machine learning technique? So we are going to define that. Secondly, I will offer you a brief introduction to neural nets with just the basics of this kind of machine learning technique. And after that, we will travel a brief tour for new techniques in machine learning. What are the current techniques that we use in scientific level and industry? Okay, so the main idea of this speech is to give you a basic understanding of what can you do with neural nets. Well, let's begin. Okay, so why it's machine learning? Okay, normally in classic programming, we have data and we have rules. Okay, data is what we can measure, and rules it's the mathematics that we know that rules this kind of data. For example, if you have a dynamical system, the data could be the initial conditions of or the parameters of your system, and the rules could be the mathematical model that you have. So with classic programming, we operate the data with the rules and we get the answers. In these examples, this system can be simulated, and we can simulate the system and get prediction about the behavior of the system. But in machine learning, we don't really have these rules because these rules needs to many years of research. No? So the idea in machine learning is that we have the answers. We can measure some physical phenomena. We can have also the data, the initial states. So machine learning will give us the rules that map the data to these answers. So this is the basic idea. It's not really the unique way to define machine learning. This is really just supervised learning. So by observing the model, the system, we can extract some information about it. That is the rules that we have. A very basic way to understand this is that we have data and we have answers, what we can measure of the system, and we have a learning algorithm that will manipulate this model. And this model is just a very general mathematical model that can approximate many things. So the idea is that the learning algorithm can move these knobs in the model, can move these variables, these parameters, and with that, we can have a representative model for this system. So usually we have models without parameters that is called Bayesian techniques, but we are gonna focus in parametric models. So that's machine learning in a soft speak. Let's make a good definition to know when a computer program is a machine learning technique. So this definition is from Tom Mitchell in 1959 and says that a computer program is said to learn from experience E with respect to some class of task T, and performance measured by P, its performance at the task T, measured by this performance metric, improves with this experience. So with that, every program that you can write that improve the performance of any task, when you push data inside it, you can call it a machine learning technique. So there's a bunch of these kind of techniques of many, many flavors. So it's a very short introduction for machine learning. Well, neural networks are just one of these techniques of machine learning, but they are very popular. They became very popular in the last 2-3 decades. And the idea in neural nets is that we are inspired by how the brain works in animals. In the beginning of this, Santiago Ramón y Cajal was the first man to describe the structure of the neural system. And before him, we just thought that the brain was very, very complex organ. But indeed, he discovered that all was built with these essential units that are called neurons. So how is it possible that we can achieve a very complex behavior in animals just with these basic elements of computing? Well, the idea is that with these basic elements of computing, we can build any complex system, and it will be defined by the topology of the network and a plasticity property that can change this topology during this evolution, and we can learn in this topology. So that was in 1906, as you can see. In 1943, McCulloch and Pitts made the first mathematical model of the neuron. It's a very simplistic model. We usually have more detailed models right now in a subject called neurodynamics, but this model is very useful for artificial intelligence. So the idea in this model was to understand how the brain works, and it wasn't to recreate the human intellect. So the idea with this is that these dendritic inputs of the neuron will be modeled with these real value variables. We can abstract this as a vector of n dimensions. And we have these synaptic ways. The synaptic ways are just the model, the separation between these neurons. If they are more separated, the possibility or the probability to excitate one to each other, it's more or less. So the idea here is that the synaptic ways would model the synaptic, and we add all these properties with an independent variable that we call bias, okay? And we pass it through a threshold function that is actually a Heaviside function. So this is a very simple model, and as you can see, it's really a linear combination of the inputs. So geometrically speaking, this neuron is just an hyperplane. But let's see an algorithm for this. So in 1958, Frank Rosenblatt proposed the first learning algorithm for this artificial neuron, and it's called the Perceptron Algorithm. It's very simple. It's just these lines of code, pseudocode, that you can see that here you have a prediction of the current neuron. We have the error, and we will use this error to get new values for W and P parameters, the weight and the bias parameters. So it's very easy. Let's see an animation of this. So as you can see here, the neuron is just represented by this blue line, and the data points is these circles, blue circles and red circles. We have two classes in this problem. So when the perceptron is learning, we can move the parameters of this line, or this hyperplane in general, and we'll adapt to separate these kind of samples. So there's no much difference between this neuron and a linear discriminator. So we can do classification with this basic neuron. So this obviously the samples are linear separable. What happens if there are no linear separables? Let me show you another animation. We had a classic problem here, a Netzer problem. It's a small problem, but it's non-linear separable. And as you can see, the line of the neuron will be moving, but will never get to a final answer. So with this neuron, we cannot solve non-linear problems. Okay. This is a huge drawback, and usually it translates to more than 15 years of drawback in this area of neural networks until someone discovered a way to overcome this problem. Well, it's a very simple network. Let's make some modification to this. What happens if I change the threshold function that we have? If I eliminate this function or I substitute but an identity function. So the result is that this output variable will be real. So this is very good because this huge architecture, or this small architecture, can be differentiable, and we can use many techniques for the optimization classics. For example, if we define the square mean metric, the square mean error, as you can see here, we can use a gradient descent for this. We calculate the gradient of the loss function and the partial derivative with respect to the bias, and we will have what thing I can move for this weight vector and from the bias. And we get these update functions that are very easy to calculate in computer. So this is a basic mathematics, the basic mathematics. Let's see an animation of this. So let me explain you this animation. I have an initial regression problem. This is a linear regression problem, very noisy, as you can see. And I have the leaf neuron adaptation. So this red line is usually what my neuron is predicting. And as you can see, I start randomly with this weight vector. So I just choose the parameters to be random. And when I'm using this gradient descent algorithm, I will surf in this objective function to get to the optimal of this. Of course, linear regression is a complex problem, so it's very easy, but this can happen in any other objective function. Okay. So what else we can do with these neural nets? We can also change it to get a probability output for this neural network. For example, if you equal the hyperplane equation to this likelihood, you can isolate P and get the logistic function. So really, this neuron with this logistic function is just a logistic regression problem that you have been studying in statistical theory. So using this, an objective function, for example, the binary cross entropy function, it's a very sensitive function. And if you use gradient descent, you will get the same update equations. Let me show you another animation of this. So this red line is our neuron, and as you can see, it can approach any categorical data. So we commonly use this logistic regression for problems of binary classification when we want to get a probability as an output. So the important here is know how we solve this problem, because all of these problems have been solved many years before neural networks. But the idea is that neural networks is a common frame for solving this kind of problems. So we change the architecture of the network and we can solve more problems than before. So that was very good, but with what network we cannot do too much. So let's stack a bunch of neurons in one layer. As you can see, we have still this vector has an input. It's an real value vector in this space, but we now have this output in this other space, okay? And we usually don't program each neuron by themselves, but we abstract the whole layer as a one. So we have this matrix, the weight matrix, that is associated to this neural layer, and it represents all the knowledge that the layer will have. So how can we visualize this layer neural networks? For example, for classification, we can see that each neuron that we have can belong to a class. So the task that I'm asking here is to separate one class from the other. So each neuron still is an hyperplane that we can manipulate independent to others, but we can get this multi-class classification. Well, logistic function is a very good technique, logistic regression, but we can generalize this with the softmax regression. That is also very old, but in neural networks, we just have to change the activation function of the neurons, and we have the same technique. So this is a classification problem. It is still linear, so we cannot do nonlinear, not yet. But as you can see, it's a very good technique. So what about if we stack a bunch of these layers of neurons? What can we do with that? So we will get a multi-layer neural network. So this multi-layer is just the stack of these layers. Here is a particular example, and it's very good to work with. And for example, the propagation algorithm is just this for loop. For each layer, I will have the input. I will propagate to this layer, and the output of this layer will be the input to the next layer. So propagate, it's very easy, but what it's not easy is to train this network, because we can get the gradient for this last layer, but in that time, no one knows how to get gradient for hidden layers. Until in 1974, Paul Werbos and other researchers get the backpropagation algorithm that get the boom to this neural network field. For example, the idea is that we can calculate a thing called local gradient just using the same weights in this architecture. So we calculate this gradient in the last layers, and we use the synaptic weights associated to this neuron to calculate the local gradient for this neuron. So with that algorithm, we can merge together gradient descent with backpropagation, and you will have this equation. With this equation, you can train any multi-layer neural network with this architecture. Okay, but we can do it, we can train it, but what we can do with them? Let's see. Well, the idea of this is to solve nonlinear problems. So consider this problem, the EDSOR problem. It's a very small nonlinear problem, and it's nonlinear in this space, in this two-dimensional space. So if I pass this data through the first layer, I will have a 3-vector in the output of this first layer. So this is just a mapping, a nonlinear mapping from the two-dimensional space to a three-dimensional space. So if I have the coordinate of the output of this layer, I can map each one of these data to these points here, okay? And the idea is that in this three-dimensional space, this network, this neuron in the last layer, is just another hyperplane, and it's an hyperplane in a three-dimensional. So I can draw it, this hyperplane, and it's just this plane in green. And as you can see, I can solve this problem, and I can separate the red points from the blue points. Okay, so this is the theory of how we solve nonlinear problems. Okay, let's see how we visualize this in an animation. So this is the same problem. In the left, you have the blue points and the red points, nonlinear separable. And in this right animation, you have the red points and the blue points, and they're moving because the first layer is approaching mapping from two-dimensional space to a three-dimensional space, trying to separate them, okay? And this last neuron in the last layer is just an hyperplane that will separate these classes. So this is the plane of the last neuron, is the same architecture. And as you can see, when we are adapting this, we will be able to separate these two classes, okay? And this plane, if you backpropagate this, or if you project this plane to the input space, you will see that this line will be nonlinear, okay? So the idea is to have points mapped to a high-dimensional space, and in this high-dimensional space, I can find a linear separation of this data. And also we can think that the last layers of this neural network can be projected, these planes can be projected as a non-linear surfaces in the input space. So this is a very simple example. Let's see a more complex one. So it's very quick, but as you can see, you start with the points together, and they sparse to this three-dimensional space, and the plane just could where it can these points, okay? So you have here how this plane can be projected in the input space, and it's just a nonlinear function. Let's see a different simulation of this. As you can see, we can solve any nonlinear problem with this approach. Well, we're gonna speak about it, okay? This is with the logistic activation function in the last layer, but we can do it for multi-class classification. So this will be the multi-layer perceptron or the multi-layer network with the softmax activation function. As you can see, these boundaries are nonlinear, and we can separate any of these. Okay. So we have shown that we can deal with nonlinear problems, but do we usually know that we can solve any nonlinear problems? Well, in fact, we have a theorem for that, no? And it's called the Kober's theorem. It was stated by Thomas Kober in 1965, and it says that a complex pattern or a classification problem, if we cast this problem in a high-dimensional space in a non-linear manner, it's more likely to be linear separable than in the low-dimensional space. So every time I map these problems to a high-dimensional space, it will be more probable that the last layer will find a good discrimination of this, okay? So it is a very complex problem. I will need a higher dimensional mapping, and this will just be a greater number of neurons in the hidden layer. Well, this is for classification. What about regression problems? So we usually have another theorem that is the universal approximation theorem that says that if we have these functions, these real functions phi, that they are non-constant, bounded, and continuous functions, this is usually just the activation function that we use. So an activation function has to ensure these constraints. Then let F be a set of continuous real value functions in this hypercube. So we are dealing with a functional space. Then for any epsilon greater than 0 and any function belong to this set, we can find an estimate function. And as you know, this kind of proof can interpolate for all the range of the reals. So this is the estimated function. And as you can see, this equation is just the same that a neural network where we have the first layer given by this and the second layer given by this with a linear activation. So we can approximate any function that is continuous. Let's see some animations about that. For example, the red line is the objective one. We have the X has an input and the Y has an wished output. And as you can see, it's very easy for the network to approximate this kind of functions. So in theory, we can approximate any continuous function. Let's see a more complex one. So as you can see, very easily the network can approach this. There are some problems here in the middle, but that depends on the number of neurons that we have. If we increase the number of neurons, we have a very good approach to this, but this is a kind of dangerous because if you have a lot of neurons, you also will understanding the randomness of the process. And as you may know, all the processes that we are dealing have random inside it. So we don't want to learn the randomness and just the pattern itself. Let me show you another example that is usually a 2D regression problem. Okay. Same neural network, but with more outputs. And as you can see, we can approximate any of these kind of surfaces. So we have a regression and classification, and we can ensure that all of these kind of topics can be solved by neural networks, just moving how many neurons we have in the hidden layers. Okay, that was the introduction. We finished, but let's now explore the neural nets. Okay, let's see what is new in these neural networks. So before that, let me tell you a bit of definitions. We are dealing right now with feed-forward networks. This is a kind of networks that the input is processed through the output. This means that the output depends only in the input that we have. Okay, we'll just consider this by now. And we call deep if this network have a lot of layers, and we call shallow if this network have a little number of layers. So deep learning is just a rebranding of a neural network. Okay. Well, let's see what we can modify for this normal scheme. We will go to, or we will get new kinds of neural networks. For example, one thing that I can move in this neural network is the optimization technique. We have seen using gradient descent how to optimize this weight, synapses, and bias, but we usually have many research in optimization algorithms that are suited for this kind of neural networks. For example, this is a work for us in 2020, where we create a new algorithm. It's called a CADAM, and it's a modification for the ADAM algorithm by using the standard Kalman filter. Maybe you know these equations. So this is the standard Kalman filter. Is just a technique for finding hidden state in a dynamical system. So with this, we can filter all these gradients that we are calculating in this standard neural network, and we have this new algorithm. And as you can see, we can get better solutions than other algorithms. Usually, what we had seen is just the stochastic gradient descent that doesn't have a very good performance. So there are many people working in this, many research groups that are making new algorithms that work better, that can work in parallel in neural networks. So it's a huge research area too in this topic. Other thing that we can change in the standard neural network that I told you is how we value, or what are the values that we get into this network. For example, we usually talk about real value neural networks. So why cannot input some complex value? So if you input some complex value, you will get the complex value network. And these kind of networks are very interesting, and they have many applications in data processing, in image processing. So they're very interesting to work. And we can also change this complex to other hypercomplex numbers. For example, we can have networks that each input will be a quaternion. And this is the architecture that we will note. They are very used in dynamical systems. For example, here is an application for multi-stability analysis, and they are very good to study the stability of a system. Usually I work with some of these kind of neural networks. I work with Clifford networks that are networks that have elements from a Clifford algebra. As you may know, a Clifford algebra is a kind of extended Grassmann algebra, very close to a tensor algebra. So in this kind of network, each one of these input is a multivector. So a multivector is just an abstraction that could be a vector, a scalar, a matrix, or something like that, very close to the definition of a tensor. So this is a multivector, and this is a whole neural network, or sometimes we call it a geometric network. In this work that I presented in 2017, I developed a new kind of neuron working in one of these algebra. And this neuron is represented by this equation. Okay. The good thing here is that this neuron represents an hyperellipsoid. So this hyperellipsoid becomes our neuron. I mean, instead of having one plane has a neuron, I will have this hyperellipsoid has a neuron. And the good thing, or the strange thing in this kind of neurons, is that this neuron can be deformed to a pair of planes or a cylinder or things like that. Any quadratic surface, I can deform this hyperellipsoid to be that. So very interesting. I'm working usually with this kind of networks. I get this hyperellipsoidal neural network, and it's just work very well for forecasting of time series. Okay, so there are many modifications that we can make. The main idea is that if you have a problem that doesn't work well with the current techniques in neural networks, you can invent a new architecture suited for this problem. And that's what I will looking for. So these problems, these architectures are very well for structured data. But what happens with non-structured data like audio or images? For that, we currently use convolutional neural networks. It's the idea of a network specialized in images. So what we use, why we use these convolutional nets? If you get an image, and an image is just this square representation with 3 channels, this is a color image, and you put every pixel to this neural network, you will have an enormous number of synaptic weights. So this network will overfit very quickly, and it will be very hard to propagate because this propagation is not made in parallel. So introducing an image to this network that we have presented, it's not a very good idea. So we took some information from the convolution operation. If you have taken some image digital precision, you have seen this convolutional operation. They are very near to the Fourier transform. So the idea with this is that you can take an image, you can take a kernel, and if you convolve these 2 images, you can output this new image that will highlight some features and will hide some other features. So the kernel will be a key for understanding how images behave. Then with this, the main idea is that we can have this convolutional neural network, and the kernel will be defined by itself by the neural net. So we will use a random kernel, and this kernel will be learned to highlight some features that are interesting for us. This is actually a very old technique. It's from 1989, but in that time we don't have the hardware that we need for this kind of networks. So they're very used today, but usually the theory is very old. So a complete convolutional layer is just like this. We have these filters. We have 3 channels for each filters. This is for working with this kind of color images. So if we convolve this color image with each filter, we will get this 2-dimensional image that is the output of this convolution. And we can put it in just one nonlinear mapping, just like a standard neuron. And this will give us this output that we can concatenate. So the main idea in convolutional neural nets is that you get into an image that is a tensor of numbers, and you will get an output of another tensor. Okay, so we will be processing this tensor to highlight some features in the image. A huge convolutional neural net is something like this. Okay, let me scroll this. Okay, so the main idea is that you will input an image and you will output a tensor, and this tensor will be convolved with many of these layers, and these layers will be understanding some primitives in the image. And in the end, we will fatten this architecture and use it and use a standard neural net. So what is very interesting is what usually it's learning this convolutional network. So we have some idea right now of what a convolutional neural network learn about the picture. There are many techniques right now. This is a technique called deep dream. So this usually is the response for one picture in the initial layer, and this is the response to the same picture for the final layers. As you can see, in the initial layers, we don't have many ideas of what we are understanding of the image. In the initial layers, we just understand some primitives about the image, like edges, colors, textures, and things like that. But in the final image, you can see, for example, here some dogs. And the idea is because we enter a dog image for this. So we have a high response to these patterns. And with this, we can study what convolutional neural networks are really understanding. So convolutional nets are very useful in practice. For example, here is a paper that we have from 2020, where we have an image for a UAV. And this is the human level image. We have to classify what is sky, what is clouds, what is ground. And as you can see, the CNN give us a very good output, very good accuracy for this. Okay, and the good thing with this is that we just need 15 human labeled image to understand all this process. Okay, so convolutional neural networks are a specific architecture for treating with images, but they are still feed-forward networks. So what other type of neural networks do we have? Usually we have the recurrent neural networks. Okay, this is not a feed-forward because the white output it depends not only about the input, but also about the other outputs that we have output in the past. So this is a neuron, this recurrent network. As you can see, we just feedback the output. And with that, we can have this as a new dynamical system. So we call all the other networks feed-forward or static neural networks. And this is a recurrent neural network or a dynamic neural network because it is a dynamical system. So to study this kind of networks, we usually unbend them to time. So the idea is to make them isomorphic to one feed-forward neural network with a huge feed-forward neural network. And with this scheme, with this unbended through time, we can train them just like any other neural network. Well, this is for one neuron. What else if we have a huge neural net? So for a huge neural net, this is the more popular technique for make it recurrent. And the idea is that I have just a one big recurrence and this A vector that is the hidden state of this neuron. The idea of this is that I can compose past states, that is this A in the past time, and with the current input, I can calculate the new state, and with that state, I can calculate the output of the network. So the main idea on using recurrent neural networks, it's giving these networks the ability to recall some patterns, to have memory, and this memory will be saved in this recurrence. Okay, so actually this architecture is very difficult to train and we don't have very good results. We use some modifications for this. The more popular technique for recurrent neural networks is a long short-term memory. And this network is very useful to operate the memory of the network. We usually have this forget gate, and this forget gate is an adaptive subnetwork that will be managing the memory of the network. So this network can select which patterns to record in the long term and which pattern record in the short term. So this is very useful until, even if it's a very old technique, in the practice and in science is one of the most used recurrent nets. Well, another new topic in these recurrent neural networks are transformers networks. They are published by Google in 2017. And this is really the architecture that is currently working in many speech-to-text recognizers or language translate systems. And usually is what it's working in your Google Assistant right now. So as you can see, it's a very complex architecture. We have a lot of steps. We have attention mechanisms that they are a new kind of neural networks. We have feed-forward neural networks and many, many steps for this. So as we wish to have more power in these artificial nets, we are dealing with more complex architectures. Another architecture that we are using is a recurring high-order neural network, and we use this architecture to study dynamical systems. So the idea is that this neural network has this interpretation. Because you can see, this is just a system of difference equation. So we are working this as a discrete time dynamical system. These are the high order connections that give the names to these kind of networks. I'm not going to explain it right now, but we can train this network with the standard command filter, and we can train it online, and it's very, very fast. The idea with this is that we can observe any dynamical system that is observable, and we can get some identification of this. For example, here you can see some experiments. This is for a robotic. We usually don't have any sensor for the position and for the position in Y and X. And we are really just comparing with the reference what we have made the robot to do. And this orange and yellow line, it's what the dynamical system of the neuron has understand. So the main idea here is if you have a dynamical system, you can put this neural network to understand the dynamic of this system and approach this dynamic. So the final neural network will be approximating this system, and we can observe the system, we can control the system, or just identify the system. Well, all the networks that we have seen are called discriminative neural networks because their work is to make regression or make classification problems. There are another kind of networks that we call generative neural networks. The idea with this network is not to classify or do regression over a data set, but to generate new data that are consistent with the old data. For example, this is the variational autoencoder, one of the most successful techniques. And the idea is that you input some image, for example, and with this architecture, the output, the widget output will be the same image. So these are non-supervised learning techniques. The idea with this is that we compress this image and these patterns in this small dimensional space that we call latent space. And this latent space is a representation for these images because we can reconstruct them. Let me give you an example of how this latent space looks like. So this is a latent space for this character handwritten. As you can see, here we have the classes of these images for every number, but this space that it's compact, that's what is doing the variational autoencoder, compact this latent space. And if you graph this space, you can see something of this, and you can interpolate between many patterns between them. So the main idea of here is that we can compress any pattern that we have, and in this latent space, these different patterns would be merged and correlated. So it's very interesting to study the latent space of a data set and see what can we do with it. Many applications we can make with this. For example, searching an image with another image, we can do it with this kind of latent space. Another network that is also generative is the Generative Adversarial network. It's currently the most popular technique for making or generating data. And the idea behind it is that we have a latent space. We just select a random vector in this space, and we generate fake samples. It can be image, fake image, or it can be anything. For example, it can be some music composed by this neural network. And we actually have real samples. And we will feed a discriminator network. This is another neural network, which task is to correctly select which one of these samples are real and what are fakes. So this network is really trying to understand how to detect fakeness in images, and this G generator, it's trying to understand how to cheat the discriminator. So usually this is an example of competitive learning. You can model this problem as a minimax optimization problem. What we can get with this kind of architecture, for example, we can merge two kind of faces. You have here your source faces, okay, and you can map it with the characteristic of these faces. So you can interpolate a realistic photograph of these faces with this neural network. And this is just an example because there are many applications that we can make with this. We can create music, we can create patterns for this. We can actually create dynamical systems that behave like a real one. And then this is the idea behind these networks. Okay, so that's for the tour for these new techniques. I hope you enjoy the travel, and I will be happy to answer any questions that you have.
Okay, thank you very much.
Thank you, Thomas.
Okay.
Let's see whether there are questions.
Yeah, we don't have any questions so far on YouTube. So if anyone here wants to ask something.
Okay.
Well, I mean, I have a question. I think it's an old question even, so which was on my mind for some time, and maybe you have heard about that. I wonder whether one has discussed, or this problem was discussed. So suppose that you have just a neural network in front of you and you're allowed to, say, use it. So to put input data and to get output. Is there a systematic, but you don't know what kind of network it is. Is it possible in some systematic way to get information about that network, what it does?
Yeah, it's like studying a network. If you think it's a black box, no?
Exactly, yeah.
Yeah, I think you can do it. Put in another network that approximates the knowledge that this network has. Usually in some subject that is called modular networks, we are doing that. We put a huge neural network, these deep learning machines, and we put little networks that are stealing knowledge from these huge neural networks. And these small networks give us an opportunity to study what kind of learning have the big network, or how transferable is this knowledge from the big network to a small network. And we are currently using this kind of features to train for a particular problem, stealing knowledge for the other network. But totally to know what it's doing a neural network, it's very, very difficult.
Yeah, or maybe, you know, whether you can know somehow whether this neural network has already been trained or not.
Yes, because if you input a pattern in the network, we can study the output of each filter, for example, in convolutional neural networks. And we can check this pattern with known features. So the idea is that you have a neural network that is not trained, you just gonna see some chaotic or some randomness in their outputs. I don't know if that
case, but you would have to know something about the patterns, right?
Yeah,
So you have
a priori, you know,
to use appropriate patterns to learn
that
something.
you know and that you can extract features.
Yeah. Okay. Thanks.
Thank you, Thomas.
Yes, Laura has a question.
Yes. I'm not pretty sure if you say it because I have some problem in my internet connection, but what is not so clear to me is, what are your team doing? You are trying to do other other kind of back propagation, or you are using different kind of algorithms to try to do in specific problems?
Yeah, we usually made new algorithms, but they are based in gradient descent. The thing here, maybe let me go to the slide. Straight in the beginning. Okay.
Well, and you are trying to do this kind of algorithm in a problem in a specific, or you are using a lot of problems that already have answers?
Yeah, the problem here is when the neural network is very big, you have many layers. There are some problems when you train with classic optimization techniques. We call these vanishing gradients and exploding gradients. So the search of new optimization algorithms is to overcome this problem or relieve this problem. So the work here is how an optimization technique can train a deep neural network. For example, neural networks today can have even 1,000 of layers. So not every optimization technique can train a huge neural network. So the idea to search a new optimization technique or make modification of the current techniques is to find an algorithm that is robust to this kind of problems. So in this slide, we use the Kalman filter to improve one algorithm that is called Adam. Adam, if you know something about neural networks, is the most popular technique for training huge neural networks. So, but it's very noisy. If you look the gradients of the network when you are training, you will see many peaks around there. So we use this Kalman filter to filter this randomness, and we can get more quickly to this local minima. And something that is important is that we don't care for reaching the global optimum of this function, because sometimes if you get to the global optimum, you also learning the randomness of the phenomena, and you will overfit the problem. So the idea is to get to the local optimum, and maybe this local optimum is very good and learn just the pattern and not the randomness of the phenomena. I don't know if this serves to you as an answer, Laura?
Yes, thank you.
Yeah, no, thanks to you. Okay.
Okay, we have a question from YouTube, from Jose de Jesus Hernandez. He's asking, is there any framework that we can use to implement generative neural networks?
Yeah, you can implement generative in all the frameworks. You can use Darknet, Keras, TensorFlow, PyTorch. All of these networks are capable of these generative neural networks. So in all that you can get, you can do this. Okay. And thank you, Jose, for the question.
Soham has a question. Go ahead.
Yeah. So as far as I understand that you are that if you use a lot of neural network to model some pattern, then there is a chance that you get the noise. So do you have any optimal way to know how many neurons you actually want to use to feed the data, such that you do not go to so that you can separate the noise and the pattern?
No, we don't have any of that, because it's really, I think it's an open question in this. We have some measures, and what we do in practice is train our neural network with a subset of the data set and predict with another subset of this data set. And if these scores are very different, you are overfitting. If they are very close, but they are not very good, you are underfitting. So the unique thing that we can do in this moment is to use this score in the subsets of the data set, just to choose if you get a bigger neural network or a smaller neural network. With a bigger neural network, you can understand more things, but also the probability of overfitting is greater. So when we are training a neural network, we look these scores, and with the difference of these scores, we choose to increase the number of neurons or to get a smaller neural network.
So using the neural network, you are saying that there is no specific way to understand how much is noise and how much is signal?
No, because if you can understand how much is noise, technically you can get the bias optimum of this problem. Because the irreducible and random will lead you to the optimums of bias. So if you know a priori how to get the noise in this kind of data set, it will be direct to compose a bias technique for this. So I think it's an open question, and I don't believe it will be possible.
Okay, thank you.
Thank you, Sohan.
So anyone has another question? Okay, so it seems that that's it. Thank you so much for your talk, Dr. Carlos.
Thank you to you.
Okay. Dr. Gomez, do you have a question?
Yes, sorry, I just one more question. So because you mentioned the different packages, right? That there are for. So what is the package you are using, or do you use your own, say, software?
Well, it really depends of the application. If we want to make a very quick predictions, we can use C++, programming this neural network from scratch, or using darknet or other framework that runs in C++. But in the meanwhile, the more used technique or the more used framework in the industry is PyTorch and TensorFlow. So in the industry level, we use both of them. In research, for example, for this slide, we code all the network from scratch, because we have to move everything of this. But usually we already code this for Keras, and you can use this optimization technique for Keras also. Okay. So as a science research, we want to do things from scratch. In the practical sense, in the industrial sense, we use these frameworks from Google and from Facebook.
Okay, thanks.
Thank you. Okay, Sohan, do you have another question?
No, thank you. No.
Okay, don't worry.
Okay, so again, thank you so much for the talk, and everyone to attend to the talk.
No, thanks to you, and thank you all for your patience and for your time.
Okay, well, many thanks.